Okay, this is part 2 in my little video series that'll help you with your summer assignment, as well as some of the review of the pre-AP material that you're going to need right on day 1. So let's get started. This is going to be covering 9 through 15, as well as your common polyatomics. Okay, so starting with number 9, I'm basically just asking you to go ahead and label, color code your periodic table so you can remember those main groups, things like their charges and the periodic trends, as well as which ones are your metals, which ones are your nonmetals. So what we're going to start with is let's go ahead and label our different groups, okay? Remember, groups are the ones that are going up and down. Let me scooch this over so we have some room. Okay. So groups are going to be the ones that are going up and down. Okay. We also like to call these guys families. So these are usually ones that start having some of the same properties and characteristics, but these guys are up and down. Okay. Your periods are the ones that are traveling across. Okay. Those are your horizontal things on the periodic table. Okay, so when we go to label our group names, I gave these all to you up here, so you just have to really color code it. So I'm gonna go ahead and get on a highlighter here. I'm gonna highlight this first column right here. Okay, and please know for alkali metals, hydrogen is not actually included. I should actually erase that here. Okay, but it is in group 1. Okay, but hydrogen and helium kind of have their own set of rules sometimes. So, all right. The next group that we've got is we have our alkali earth metals. So group 2 is your alkali earth metals. Then we're going to have these guys right here in the center. Let me see if I can get it. All right, there we go. Okay, these that are traveling across, as well as these that are going to end up getting put in there. Okay, these are your lanthanide and this is your lanthanide and actinide series. Okay, however, they are, remember, inserted into your periodic table to make to be part of the transition metals. But these are going to be your transition metals. Then we're going to go into our nonmetals. Okay, so we have, let me go back to yellow. So our nonmetals start, if you remember, at our little stair step that we have. Okay, so we have this. Anything touching the line is considered a metalloid. Okay, and then things on this lower side are continuing to be metals. Things on the upper side are our nonmetals. Okay. Things about transition metals. So their charges tend to be kind of all over the place and crazy. So some of them have multiple different charges. All right. And we will go over that a little bit more, I think, on day 1. I'm not going to kill you with it in this video. But if you have a chance to look them up, start memorizing a few of your main ones, such as like zinc and the iron and cobalt. Okay. And there is a little trend that you can remember them with. So just start looking at that. All right, and then last but not least, we have this guy over here, which is your noble gas line. Okay, so those are your different group names. When you have this one where we say it's group 3, 3A, and then we have 4A, and then we have 5, all of those, 5A, 6A, 7A, and then AA. What we want you to call those is this would be the boron family. This one would be the carbon family, nitrogen family, oxygen family. And when we get here, this group 17 right here, okay? Remember, these are your halogens, or halogens. Hopefully you guys can see that. That kind of finishes it up with our different group names. Next, what we've got is we're going to go ahead and label metals. And these will be nonmetals. metals. Okay, so we've now taken care of the first one. We've done group names. Period, we are just going down. So we say 1, 2, 3, 4, 5, 6, 7. Okay, your different periods are going to be important because these are also talking about your energy levels. If you remember back to the different orbitals and when we did orbital notation and just how many different shells are around it. So just remember that for period. Those are usually telling you your different energy levels that you're out. And then obviously as we go across, so our different groups are talking more about number of valence electrons for our main group elements, and then just kind of focus in on them being showing you your different electrons and increasing that number to the right. Okay, so we've got periods, we haven't done charges, we did metals and nonmetals. All right, so what I'm gonna do here is let me do kind of a purple. All right, so what we're gonna do is I'm going to go ahead and start putting the different charges of your main group elements, all right? So when we say main group, we're kind of eliminating all of my transition metals, okay? So when we look at that, our different charges or oxidation states are going to be +1, meaning I have an electron that I can give when I go to bond, okay? I have +2. This is +3. Carbon, we like to say, is ±4, kind of go both ways. He has 4 electrons, so lots of things bind with carbon, especially for our organic stuff. Nitrogen is going to be considered a -3, meaning it has a deficit of 3 electrons, so it can bind with 3 things. And then oxygen is a -2, fluorine is a -1, and then noble gases do not have that charge. Okay, these guys are good to go. So those are our charges, the periodic trends. Okay, so what I'm going to do is I'm going to shrink this whole thing, kind of shove it up here. I'm going to draw myself another little periodic table down here. Okay. And don't judge me on my drawing. We'll go up, lower, there we go. All right, so this is your periodic table again. So just a reminder of what your trends are. When we are talking about atomic radius, okay, atomic radius, we are looking at a very small corner and a very big corner, meaning as you move to the left and down, you are getting bigger, okay? So when we look at that, that tells us that francium has the largest atomic radius, whereas something like fluorine has the smallest, okay? So that's your atomic radius. Please note, the reason we're getting bigger going down these periods has to do with those energy levels or shells. So this is due to increasing number of shells, okay? If we're looking at periods, that's what we're doing. If we are looking across the periodic table, okay, we are increasing number of protons and therefore squeeze in our electrons, meaning as I have more positive charge in the center, I'm going to be pulling in all those negative things around me. So that's why we're going to get smaller when we get here, and we're going to be looser when we're off on this side. Okay? Okay, your next trend is going to be, let me kind of move this up just a tiny bit here. Your next trend is going to be your electronegativity. Okay, so electronegativity is talking about how much you're going to be, I hate to use the word desiring electrons, but it's going to be how bondable are you? It really has to do with when you go to bond. And so like I said, it's how much it's going to be attracting a pair of electrons when you're bonding. So knowing that, what you kind of can ask yourself is, who wants the electron the most? And that's going to be fluorine. So what we like to do for this one is we put a nice big heart on this side, and we put a tiny little heart on this side. And that's going to be talking about your electronegativity, okay? So that's electronegativity. So the last one that we're going to chat about real quick is going to be your ionization energy. And I like to relate electronegativity and ionization energy because ionization energy, the definition of that is the amount of energy needed to take away an electron, right? So energy needed to take away an electron. So you can kind of go back to that idea of how much do they love their electrons? How much are they holding on? Fluorine is going to have the highest ionization energy, and francium is not going to be holding on as tightly. Francium has a whole lot of shells, right? A whole lot of energy level. So it's huge, okay, with a little nucleus right here. So the communication between the nucleus and an outside little electron is very small. It's going to let go of an electron pretty easily. Fluorine, on the other hand, right? That distance there is so small, and fluorine has a lot of a lot of protons as it moves across, right? So everything on the right-hand side of the periodic table kind of has more protons than on the left-hand side of the periodic table, and therefore that they pull in really, really tight. Okay, so that's your ionization energy. The only other one that you also want to know is going to be their Ionic Radius. I know I didn't add that on there, but I would make note of this just on the side is Ionic Radius. Just remember that when I talk about an ion, that means it's a charged atom. So if I get rid of an electron, I become more positive. If I take on an electron, I become more negative. So things like sodium, okay, when he becomes sodium minus his electron that he gave away, okay, you're looking at a big thing going down to a small thing, all right? So as I become more positive, I get smaller. Or if I get rid of electrons, I become smaller. On the other hand, if I have something like fluorine and going to fluorine -1, so he takes on an electron, we're going from something small to poofing out really, really big. So an easy way to remember that is if you get rid of an electron, it's like you throw up an electron, right? And so you get a little bit smaller. Your stomach, you don't have as much in your stomach, right? So if you gobble up an electron, you're gonna get fatter, all right? And that's an easy way to remember it. But those are your trends. I believe we hit everything that we were asking for, so we're going to go ahead and move on. Oops. Okay, so this next slide, we're going to be going over 10, 11, and 12. All right, so number 10 is talking about nuclear notation, okay? Nuclear notation is something you learned at the beginning of pre-AP year, and then we kind of expected you to remember it, but you do need to be aware of that because sometimes they're going to give you questions where the information that you actually need to answer the question is within that nuclear notation. So what I want you to know about this is that, so for example, for that one that we have up there, actually no, we're going to do a different one. We're going to do sodium again, okay? So if I have sodium, all right, and sodium has an atomic number of 11, that goes on the lower left-hand side. And then the top number is your mass number, all right? So mass number, if you remember, is protons plus neutrons. Usually, we tend to have the same number, right? So for sodium, we could say 22, okay? And this is like a normal one where we have, and if you notice, there's nothing up here in the right-hand side either, okay? So what we have here is we have a sodium atom, okay? This will always be your atomic number. This is your mass number. So protons plus neutrons, okay? He has 22 protons, neutrons, and electrons, and that's it, okay? If I were to change this up, if I were to do something like an isotope, so I said 23 with 11, we would still be talking about a sodium atom that would have ooh, I messed up. I'm so sorry. This should not say 22. That's something looked odd up there. This should actually be 11 for each of them. I'm so sorry. We should be going with the atomic number. Silly mistake on my part. But all right, so back down here, we have sodium. So here we are going to have 11 protons. You'll have 12 neutrons and 11 electrons. Okay? If we were to take it one step further and now talk about something like an ion, okay, we would have something that looks like this. So we could even leave the isotope of 23, and then we could turn this into, we'll go like that, okay? So now I have my sodium ion, which is what we usually deal with. So we have 11 protons, we still have 12 neutrons, but according to this, my charge is one less electron. So I no longer have 11 electrons. I'm going to actually have 10 electrons, okay? So I do want you to be pretty familiar with your nuclear notation and what information is given to you in those kinds of questions. So looking at the ones that I assigned you, we can see that I have silver. Ag is silver. You can verify the 47 from the periodic table. So we have our atomic number of 47. Okay. Atomic number is always your protons. Atomic number, always protons. Okay. It will never not be that. We can't mess with the protons. Okay. So back on this, we're going to say we have 47 protons, okay? The way we figure out neutrons is we're going to look at our 109 that we have there. So if we take 109 minus 49, you're going to get 60 neutrons, okay? And then for electrons, since there is no charge given up here for either of these, you're going to have the same number as your protons. So we're going to have 47 electrons. If I would have given you a charge, then you do want to take into account doing what we did down here, okay? Over here, I think you can handle the next one. So moving on, number 11, okay? Number 11, I'm just kind of get this stuff out of the screen for now. So we have some room. Okay, and number 11 says when a metal and a nonmetal combine, this is called an ionic or molecular compound bonded by blah, blah, blah. All right, so metal and nonmetal. When we have metal and a nonmetal, you're kind of thinking of a positively charged thing and a negatively charged thing, okay? When you have a metal and a nonmetal, it is always ionic, meaning electrons are actually transferred, okay? So electrons transfer. They're not shared, okay? And when it does that, that's actually what creates that positive negative thing. So if you have something like sodium chloride, right, he gives his electron over here, so this now has a net negative and a net positive. Okay, and that net negative and positive are going to now attract to each other, kind of like magnets, okay, with electrostatic forces. So you can kind of think of static electricity. That's what it's talking about. That's exactly it, right? Positive and negative things coming together. When a nonmetal and a nonmetal are going to combine, this is a molecular compound. So this is when we have And a lot of people like to say a covalent, and that's fine, but you're going to see molecular more often, all right? But this is when you have a covalent bond, okay? And electrons are shared for this one. So this is where we, when in pre-AP year, you had to learn about all the different shapes, and you have to make sure you draw in your bonds, okay? So something like CH4 methane, right? These are all bonds. These are all covalent bonds. This is a molecular compound, okay? And so it's bonded by your covalent bonds. Okay. All right, so moving on. Hopefully that was a nice little review. Oh, and just metallic bonds, please know your metallic bonds is when you have a sea of electrons. Okay, so the electrons are basically delocalized. So delocalized is the special fancy word, meaning they kind of bounce around to all the different metal atom or nuclei. Okay. All right, so next part, number 13, we're going to be naming some compounds and then labeling them as ionic or molecular. So let's go ahead and start with labeling, because that's what we just did. So we're going to go ahead and look at this first one. And with ionic, you want to start thinking metal, non-metal. Molecular, you're looking at it non-metal, non-metal. Okay? So for this first one, we have sodium chloride. All right, so we have a metal and a non-metal. You should be looking at a periodic table while you're doing this, and you should be, the one that you just colored on the other page, you can look at that and see, is it on the left-hand side of my metalloids line, that little staircase that we did, or is it on the right-hand side? That's your basis, okay? So sodium chloride is definitely ionic. The next one we have is potassium sulfide. That is also going to be ionic. The next one we have is nitrogen monoxide. That is a nonmetal with a nonmetal. So this is going to actually be molecular. And same with these last two. So let's go ahead and now write the names. So you kind of already heard me say them, okay? When you are naming your ionic compounds, okay, you're going to go metal, and then you're going to say your non-metal ide. Okay, so here my metal was sodium, my non-metal was chlorine, but we're going to take off the ene part and we're going to make it a chloride. Okay, so all those halogens are going to turn into ides, or halides, I'm sorry. Okay, this next one, potassium sulfide. So once again, my metal was potassium, my non-metal was sulfur, but I'm going to change it to an ide ending. All right, my next one, we had molecular. When you have molecular compounds, okay, you're going to be using prefixes. And the only catch to that is no mono on first element, okay? Any other time you're going to be doing that. So you're just going to basically name it in the order that it's shown to you. So here we have nitrogen, because we're not going to put that mono on there. So we have nitrogen. We have one O, so I'm going to say monoxide. Make sure you look up your different prefixes. That's an easy Google search. Just write them down on your own. Okay. The next one we've got is nitrogen dioxide. And then finally we have dinitrogen. So if you notice, we had to add that prefix to the first one because there was more than one. And then this is going to be tetroxide. Okay, so you've now seen me use mono, di, You should know tri is next. Then it goes tetra, penta, hexa, hepta, octa, nona, deca. Okay, so that's kind of all of them together. You, like I said though, just do a quick Google search, you'll get them right there. All right, so looking over at the other side, we have the first one, we have calcium, and then we have some bromine. That is a metal with a non-metal. Okay, so let's go ahead and just name it. We're gonna say calcium bromide. Okay, these guys are main group elements, so you're not gonna have anything like your Roman numerals. We'll go over stock system in just a second. Just a reminder, okay, pay attention to your subscripts. Like, where are they coming from? This subscript right here is coming from the fact that calcium has a +2 charge, bromine had a -1 charge. You crisscross your charges, and that's how we come up with your formula, okay? All right, so the next one, as you can see, copper is actually found in the center of our periodic table. It's a transition metal. So we can't just say copper nitride, okay? We actually have to go and look at which copper we're dealing with. So I like to always do a quick reverse crisscross, okay? And what we see here is we would have, oh, just so you know, this is ionic, and this is ionic as well. Okay, so when we do that reverse crisscross, you end up seeing that we have copper +2 and we have nitrogen -3. What you do after you do a reverse crisscross is you check, is this a correct statement? And if you look on our periodic table that we just colored, nitrogen does have a -3 charge. So we get to leave this alone and we just pay attention to this. Okay, your charge is now going to become a Roman numeral. So this becomes copper 2 nitride. I'm going to run out of room right here. There we go. Okay, so copper 2 nitride. Okay, now we've got SO3. Biggest mistake that people make on this one. Okay, biggest mistake that people make on this one is they think that that's something like sulfate, or sulfite, I'm sorry, sulfite. But it is not sulfite if it does not have a charge. If you notice, this is just SO3, right? If it was SO3 with that -2, this is sulfite. That's a polyatomic ion, which we're going to end our video with. This is just a molecular compound. So we're going to go ahead and label it molecular. We're going to say sulfur trioxide. Okay? Sulfur trioxide. P4O10, if you look it up, is actually phosphorus pentoxide. It's based off of a P2O5, but just for our purposes, we're gonna call it as we see it. And what we have here is we have 4 phosphoruses and 10 oxygens. So I'm gonna go ahead and label this as molecular. And if we were to label it with the rules that we know, we would say tetraphosphorus, okay? And then we would say deoxide for our 10, okay? And then finally, our last molecular guy is nitrogen trifluoride, okay? So just a reminder, your ionic compounds have metal and nonmetal. So you say metal, nonmetalide. Molecular, you use your prefixes, but no mono on your first element. And then finally, your stock system, okay, is going to always be ionic. So you're going to use the same idea. You're going to say metal and nonmetalide, but we're going to add in a Roman numeral. Okay, and that Roman numeral is the charge. So what I like to do is I do my reverse crisscross like we did back here. And I figure out, is my anion correct? If it is, then cool. Another way that some of you guys learned it was we also taught you to say, so going back to that same example, is you look at your anion. Nitrogen has a -3 charge. So if we have a -3 times 2, that means we have an overall of a -6. So what you're going to say is we have a -6 over here. This one has to be a +6. So we're going to say 6 divided by 3 is 2. And that's where that Roman numeral 2 came from. Okay, that was the longer way. And basically, if my nitrogen didn't match up, this is the way you need to do it. You need to figure out what is that charge. Okay, number 14 is just asking for writing the chemical formula of each substance mentioned in the word descriptions. We will try to take it one more step and actually write out the different things, but you can kind of use your list for your polyatomics if you don't have them memorized yet, but you really need to work on it, okay? But we have zinc carbonate can be heated to form zinc oxide and carbon dioxide. So we have zinc carbonate. So I'm just going to put my basic idea of each of these. So carbonate is CO3, and I know he has a 2-. Zinc is a transition metal. So there's a zinc 1, there's a zinc 2. So I'm going to go ahead and make this just be the +2 one. And so if we were to crisscross everything out right here, you would be left with zinc carbonate, okay? And it's heated to form zinc oxide. So if we're going to stick with our +2, this guy already has a -2, so we're good here, plus carbon dioxide, okay? And so now we're done. Okay, the next one says on a treatment with hydrofluoric acid, silicon dioxide forms silicon tetrafluoride and water. So this one we are looking at basically hydrofluoric acid is part of it. Okay, so we'll go over acids in a second, but remember acids are led with an extra hydrogen in the front. Okay, they're different protons. We're going to say silicon dioxide. So silicon is Si, and silicon is in the little carbon family, okay? And we don't have to worry about charges for this one because they are both nonmetals. So we're going to say silicon dioxide. It's going to form silicon tetrafluoride plus water. Okay, and if you want to take it a step further, go ahead and balance this out so you get some practice doing that. And if you want to verify your answers, you can message me. All right, next one is sulfur dioxide reacts with water to form sulfurous acid. So sulfur dioxide, SO2, plus some water is going to react to form sulfurous acid. So what we're about to go over on the next slide is going to be how we name those. But basically you either have sulfuric or you have sulfurous, and we can actually go even further than that. But for now, with ic and aus, basically this is going to take on the sulfate, okay? Polyatomic. Sulfurous is going to take on your sulfite polyatomic ion. So what this tells me is if we have sulfurous, then what we're going to have is, and both of these have a -2 charge. Sorry, my bad. Okay, so what we're going to have is we're going to have H, and we're going to say sulfite, right? -2 plus 1, crisscross, we end up with H2SO3. Okay, keep practicing, look up things if you don't remember exactly, or start asking me questions as soon as you can if you don't really remember how to name things. But basically naming is just going to come with practice. It's the best way to do it. There's no quick way except just memorizing your rules and just applying them and applying them and applying them, okay? All right, let's on to the next one. So now we're going to be naming those acids. Okay, and I kind of gave you guys a little hint up top where I said binary. You're always going to say hydroic acid. So binary means 2, right? Ternary is more than 2. Okay, and so the binary ones I would say are super easy. Okay, and I think I only gave you 2. Yeah, it looks like I only gave you 2. And this first one is actually a trick question. So this one, and just know, since it's in gaseous state, you actually do not call it an acid. We're going to call it hydrogen chloride. Okay. When it is in an aqueous state, then we can call it an acid. And this would be now hydrochloric acid. Okay, so as you can see, I did hydroic acid. That's my binary. On the one on the page before, you saw hydrofluoric acid. Okay, there's things like hydrobromic acid, hydroiodic acid. So you can do a lot with that. Your ternary is when it gets a little more confusing, okay? In that one, you're going to be dealing with your polyatomic ions, which, once again, I'm going to cover on the next page on how to memorize them. Otherwise, you should just have a picture or your little list of your polyatomic ions. What you're going to be doing is, if you have something that ends with 8, okay, you're going to be using the ic ending. If you have something ending with ite, you're going to be using the aus ending, okay, and then everything before it. So you're still going to do, you're not going to do the hydro. So the hydro now goes away. We don't care about that. We're just going to say your cation, ic or aus, acid. Okay, so looking here, we have, I'm sorry, I should have said anion, not cation. But looking at the first example, we've got ClO4. So I want you to take a look at your little polyatomic list. ClO4 is going to be perchlorate, okay? And I'll go over what the per means in just a little bit. But it is perchlorate, right? So ClO4, and it has a -1 charge. This is perchlorate. So what you're going to do is we're going to keep the whole beginning. We're going to chop off the 8, replace it with an ic, and say acid. Okay? So now we're going to have perchloric acid. Okay? Same with the next one. So now we have H2CO3. CO3 is carbonate. Okay, so what we're going to do is we're going to get rid of the 8, replace it with an ic, and end with acid. This is carbonic acid. Okay, next one we've got is ClO. Okay, ClO, just so you know, is, so we go perchlorate, then we have chlorate, then we have chlorite. Now we're going to have hypochlorite. Okay, so we're going to say hypochlorite. We're going to replace the ite with an aus. Okay? Hypochlorous acid. So hopefully you're kind of catching on how we're doing this. The next one, we're dealing with a sulfate. So this would turn into sulfur. Remember, sulfate turns into ic. So ic acid. The next one we have sulphite. So this will be sulfurous acid. And then finally we have phosphate. And phosphate is going to be phosphoric So that's the basic in a nutshell, how to name your different acids. And okay, so finally this leads me to the big one. This is usually one of the harder things for a lot of my AP students to do, and that's to memorize your polyatomics. Because you look at this list and you're like, this is a little overwhelming. So this list right here is what you guys all had pre-AP, or you were allowed to use it all the time, but I started encouraging you to try not to. These two lists are actually the same exact thing. So they're listed in alphabetical order on whichever one you want to memorize. So you either memorize the names or you memorize them by their formulas, okay? But you do want to get to know these. So what I usually teach is how to make it a little bit easier, okay? And I'm going to focus in on the little sentence that you have right there. And that says, Nick the baby camel ate crates of inch clams for supper in Phoenix. So what this little saying does for you is it tells you all of your eights. All right? So we're going to start by that. This tells you your eights. Now, before I continue on and tell you the rest of this, the next thing you need to know, you need to kind of memorize, get yourself used to it, okay, is that it always goes per 8, okay, 8, ite, hypo, ite. Oops. Hypo, ite. I'm having trouble writing today. Okay, there we go. Okay. And so what this does is this is your number of oxygens, okay? There is no set, all the per 8s have 4 oxygens. That's not something that you can rely on, which is why this gets so frustrating. So what it means is the number of oxygens. Let's just say for my 8, I had 3 oxygens. My per something 8 would have 4, this would have 2, this would have 1. Let's just say my 8 started with 2. Okay? I'm sorry. Let's just say it started with 4. That's better. 4 would go down to 3 and 2, and then it would go up to 5. So we're counting the number of oxygens. I like to base mine around 1. Because once you know 1, you now know 4 of your polyatomics just by memorizing 1. Okay? The next little helpful rule is that usually in your, at least in your group, so group 17, they all have the same charge. Okay? And for the most part, you can kind of memorize your charges somewhat that way. Okay, so once you know 1 in that column, usually you know it. There are a few exceptions to that rule, but at least this will get you going somewhere. Okay, and I'll show you what I mean by that in a second. All right, so let's go ahead and look at the sentence now, this goofy little sentence. This sentence tells you your 8s, like I said, okay? And each one of those words represents one of those 8s. So Nick represents nitrate. Okay, nitrate. And what you get from this word right here is your number of vowels is your charge, is your negative charge, I guess you could say. Your number of consonants is your number of oxygens, okay? So using that, we can now say nitrate, okay? We know that it has nitrogen. We know that there's some oxygens, right? Looking at Nick, we know there are 1, 2, 3 consonants. So we're going to put a 3 here. There's 1 vowel. It has a -1 charge. This is nitrate. Now that I know that that's nitrate, I can now say, we can say per nitrate. Okay, which would be NO4 -1. We can go nitrite, by taking away one of the oxygens, so NO2 minus 1. Or we can say hyponitrite, and that would be NO with a -1 charge, okay? So as you can see, what I just showed you was that using this one word, I have now memorized 4 polyatomics. Easy, okay? And that's why I love this sentence so much, is that it allows you to memorize a good chunk of what I'm asking you to memorize without much work, okay? And it's okay if you don't memorize the sentence in order, as long as you memorize what the words are. Some of the words are. You can usually figure it out, okay? And know that your number of vowels is the charge, number of consonants is always your oxygens. So Nick is going to be nitrate, okay? Baby is going to be borate, okay? Camel is going to be carbonate. 8 is just a reminder that you have 8. Crates is chromate. Inch is iodate, so iodine. Clams, chlorate. And then supper is sulfate. And then phoenix is phosphate. So as you can see here, okay, if you know this sentence, you now know 1, 2, 3, 4, 5, 6, 7, 8 times 4. You just memorized 32 by knowing this sentence. So that's why I really recommend getting comfortable with the sentence. If you'd like some help on that, just message me. Obviously, according to our list, it doesn't cover all of them. So some of them, it's just going to come once again with practice. You'll kind of start... if you Google how to memorize them, there's another way out there, and I'll try and put the link up today, that somebody actually has you memorize where they're located on the periodic table, and it does like a 4, 3, 2, 1 thing. And so that works for some of my students. But this is what I usually use because it gives me 32 of them, and the rest of them I just look up until I become more comfortable with them. And that's the best hint that I can give you. But you do need to know your charges, okay? So it needs to be the polyatomics and their charges, because the charge is what makes them an ion, okay? So hopefully this helps. Look for another video here shortly.